Hello, my name is Tom Delord. I work as a postdoc in the group of Carlos Merlis, and today I will talk about NV centers, and in particular how to use a charge state as a memory under cryogenic conditions. So the NV center is an atomic defect in diamond, a wide bandgap semiconductor. It is widely used for quantum information and quantum sensing, thanks to its very long coherence time. The NV center has two charged states that are metastable. The NV minus state, which is mostly used for quantum information, and the NV0 state. So in quantum information, the NV0 state is mostly seen as a hurdle. What we want to do here is to use that to our advantage to store information. However, it has also implication for quantum information because it helps us understand and control the charge state dynamic of the NV center. So because those two charge states have different positions in the diamond bandgap, they will behave differently under elimination of different wavelengths. So for example, under green elimination, we will cycle through both charge states, and because of a difference in ionization rate, we'll mostly end up in the NV minus state. Now under red elimination, we will only excite the NV minus state. So it will emit photoluminescence that we can observe, and eventually will get ionized into the NV0 state. So those two wavelengths here gives us means to both optically initialize and read out the NV charge state. And so you can take advantage of this process to design a memory. For example, if you use a homogeneous sheet of NV centers, NV ensembles, you can initialize it into a bright state with a green laser, so into the NV minus state. And then if you use a high power red laser, you can selectively ionize certain areas of this NV sheet. And if you use a lower red power to subsequently read the charge state of the NV, you will observe what you see here. So the image you have imprinted with the higher power red laser. So this process is, you can repeat it, you can do several readouts, and you can reinitialize everything into the bright state with the green laser. And this has been shown a couple of years ago. However, one strong limitation is that although in every diffraction limited spot, you have many NV centers, because both your reading and writing mechanism are optical, your resolution is limited to a diffraction limited spot. So that limits the data density that you can store in a diamond using this NV memory. And so what I will show now is how, using cryogenic condition, we can use the fact that the NV minus optical lines become very sharp to beat that diffraction limit and enhance the data density of this process. So we'll first show sub-diffraction imaging of single NVs in diamond, and then show sub-diffraction charge control, and eventually leading up to multiplex storage with NV ensemble. So let's look at single NVs in diamond. What you see here is a confocal images using a green laser of single NVs. So every bright spot here is a single NV. If you look at one of these dots, you can observe the photoluminescence excitation spectrum by using a sequence when you first use a green laser to initialize the charge state on the NV into the NV minus state, and then use a resonant laser to excite the zero photon light of the NV centers while collecting the photoluminescence. And if you change the wavelengths here, you'll be able to reconstruct the spectrum. This is what we did here, and as you can see, we have characteristic features of the NV with several pretty sharp lines. Now, this spectrum is done while cycling many times through the charge states of the NV and reinitializing to the NV minus with a green laser. However, with a much lower red power, you can perform a full sweep of the spectrum with a single green initialization. So this would be the sequence here. It's a single green laser, lower power, and readout of the photoluminescence at different wavelengths. If you do that, this is what you typically observe, where here we've zoomed in on one of the two. Each of this curve here is an iteration of this full sequence, sweeping through the whole spectrum. As you can see, in sometimes we have a peak, sometimes not. This is simply because the green laser does not have a 100% initialization fidelity for the NV minus charge state. And so in some cases, we observe a peak corresponding to the NV minus charge state. In others, we are in the NV0 state, that is dark. So what you essentially have here is that if you park, for example, your laser on this line, and if you don't have too much spectral diffusion, you have a very high fidelity readout of the charge state. Whether or not you see photoluminescence tells you in which charge state you are. Now, let's look at other NV centers in this sample here. If you look at the spectrum, this is what they will look like. And as you can see, you have similar features. However, the lines are all at different positions. And that is because even though those NV centers are next to each other in the same sample, they are under different charge and strain environments that determine the position of this line. And so we can use this because it allows us to selectively control one of those NVs. For example, if we park a laser on one of those lines, only one of those 4 NVs will emit photoluminescence. And for example, we can use that to reconstruct confocal images, where, as you can see, only one NV is mostly visible. Now, what happens if you put those 4 NVs in the same diffraction limited spot? This is what you have in this confocal images. As you see, we have an elongated shape here, and you actually have 4 NVs here at the same, very close to each other. If you look at the spectrum, the PLE spectrum of that spot, this is what you get. And so again, even though those NVs are very close to each other, they still experience different electric and strain fields, which makes their line appear at different positions. And in fact, you can assign each of these lines to one of the 4 different NVs, as we've done here. And so you can do the same thing as we've done before and selectively address one of this line here to selectively address one NV. And you can reconstruct the confocal image of that specific NV using a laser parked at this specific frequency. If you do that for all different NVs, you can actually use those images to precisely determine the position of each of the NVs in that NV cluster that I've zoomed in on here. Now, again, this is done while cycling through many charge state of the NV centers, this spectrum here, using green laser to reinitialize the charge state many times. But you can do, again, a full spectrum at much lower power while being in the same charge state. So to look at that, let's focus on the right part of the spectrum here. This is one iteration of the spectrum where we've used a single green pulse to initialize the charge state and then read out the full spectrum with a low power red laser. And as you can see, so we have several peaks. 3 of them are assigned to NV2, 1 to NV1, and 1 to NV4. And notably, NV3 is absent. And that makes sense because, as I've said before, the green laser doesn't have a deterministic initialization into the NV- state. And so here, the NV3 is in the NV0 state. And so the fact that you can observe those lines independently means that you can read the charge state of each of the NVs here. And you can go further. If you use a higher red laser and you park it at one of those lines here, you can selectively ionize the NV that this line corresponds to. And if you do a subsequent low power readout, this is what you then get. You see that the 3 peaks assigned to NV2 have now disappeared. And you can repeat this process and ionize, for example, a second NV, NV1 here, eventually reading out NV4 several times until we finally ionized it as well. So what you have here is individual observation of the charge state of the NV within that cluster, as well as control through ionization. So if you think about it, here what you have is a 3-bit sub-diffraction memory. And obviously, it's not a very practical memory. And if we want to go further and increase the memory density, we'd have to put more NVs, and we will not be able to resolve their individual spectrum. So in order to do that, we worked with a much higher density sample, a 1 ppm nitrogen-doped diamond. And if you look at the optical spectrum of such a sample, you will see that it has a much broader line, about 100 gigahertz width. And on that sample, you can do exactly the same thing as I shown before, early on. If you park your laser at one frequency, you can use a high power laser to imprint an image on the sheet of NVs that you have here in that plane. So for example, here we've imprinted this image of a bird, and with a lower power red laser at that same frequency, you can read out this image as I show here. Now, however, different as opposed to what I've shown before here, if you move the frequency of the red laser slightly off the first image you've imprinted, you will address different NV centers. And so you'll have a brand new canvas that you can imprint a different image on with minimal interference. So this is what we did here at a difference of about 7 gigahertz, at a shift of about 7 gigahertz. And because this spectrum is so broad and individual NVs have relatively sharp lines, you can actually do that about 12 times with still minimum interference between two images. And so what we've done here is we've multiplexed the data storage in our NV ensemble in the frequency domain, here by a factor of 12. So to conclude, what I've shown here is that one, we can use wavelength multiplexing for optical memories. And even though here we are not quite close to the state of the art of other technologies like hard drive or SSDs, what we're showing is that it is possible with an optical memory to beat the diffraction limit. And perhaps with a different material under different circumstances, we could this could become a competitive technology as far as memory storage goes. Another thing that I've shown before is that we can have sub-diffraction addressing of the charge state in an NV cluster. And this is interesting for quantum information because the NV centers are very good spin qubits. However, it is hard to interface two qubits together. And having them very close to each other in a sub-diffraction volume could be one way to scale up quantum computing from a very good 1 bit, to a few qubits situation. So with that, I'd like to thank you for your attention, and thanks the members of the team, in particular Richard Moret, who is the lead PhD on that project, and Carlos Mireles, the team leader.